rescale, maybe rotate them and transform them to their correct positions in the virtual environment. So that requires you to be able to handle the transformations of rescaling, rotation, and translation in the three-dimensional environment. And then to produce the view of the three-dimensional environment, that is going to require you to imagine a virtual camera positioned in the environment, looking in a certain direction. And then somehow you have to get the abstract data specifying the objects in the environment. You have to project them onto a viewing screen, which is kind of like the front of the camera or so on. And again, how that is done is using a lot of translations and rotations, etc. And we'll be coming on to talk about that in detail, that whole process. But for today, this afternoon now, we just want to look at, examine certain transformations in 3 dimensions and how we're going to represent them using matrices so that we can manipulate, at the most basic level, manipulate the positions of vertices in 3 dimensions and translate them around the place, rotate them around in a 3-dimensional rotation and shrink and rescale them and so on. Okay. Now, when we were looking at 2-dimensional transformations, we also included reflections. Now, we're going to drop reflections really because if you think of the actual transformations that you can do with a 3D object, in this phone here, I can pick it up, I can translate it around in the environment, I can rotate it around anyway. I can't reflect it. I can't produce the, let's say that's a left-handed phone with the thing over here. I can't produce the right-handed version by reflecting it. It's not actually something I can physically carry out. So we're going to drop the reflections as transformations and just really consider the transformations that we're going to use to construct our environments, such as rescaling, so producing bigger versions of a basic model, translation, moving things around in the environment, and rotations. Okay. The translations and the scalings will be fairly, they just generalize immediately from their 2-dimensional version. The rotations are a little bit more tricky. There's a lot more room, I feel like a lot more room in 3 dimensions than there is on the 2-dimensional plane. Okay? So there's a lot more, the rotations in 3 dimensions have an awful lot more structure and take a bit more understanding. Okay, okay. That's all kind of introductory waffle, if you like. So we need to fix a coordinate system. Now again, we're going to use these homogeneous coordinates. But we're dealing with 3 dimensions now. So our points, any point in 3 dimensions is going to be represented as a position vector. Well, that's a vector in 3 dimensions now. So it has three components. Normally we think of a 3-dimensional vector with 3 components, an x component, a y component, and a z component. But now we're using the homogeneous coordinate representation. So we have a 4th coordinate, which is, for the most part, we think of just as the fixed value 1. Although sometimes when we rescale and so on, sometimes we may encounter the 4th homogeneous coordinate is something greater than 1 or less than 1. And in those cases, it's interpreted, mostly it's interpreted as some kind of scaling thing, so that this object u here would actually represent the point with coordinates a over 3, b over 3, c over 3. Okay. So they get rescaled by a third. But that, for the most part, that won't be an issue. For our purposes, we're really just considering homogeneous coordinates as a kind of a device so that we can represent translations using matrices. Okay. Because if we only use 3 component vectors for our 3-dimensional vectors, we wouldn't be able to have a matrix which carried out a translation. Okay. By definition, when you multiply a vector by a matrix, when you multiply the 0 vector by a matrix, it remains the 0 vector. Whereas a translation is supposed to move everything similar. So a translation should move the origin somewhere. But when you move to the 4 homogeneous coordinates, then you can use matrices to represent translations. Okay. So let's look at these. So we want to talk about translations, scalings, and rotations. Now, translations and scalings we'll deal with, extremely shortly because there really isn't much to understand. A translation in R3 is simply to move every point by a fixed vector quantity. So here we're using a translation vector D. So it's a three-dimensional vector. So we fix some D and then we translate everything in the space by adding D onto it. Okay, so any vector X will move to a new vector X plus D. And translation by D, this is just straight generalization of the two-dimensional case. This is the matrix T here, which represents translation by the vector D. So dx, dy, and dz, they're scalar quantities. They're the three components of the three-dimensional vector D, you think of normally. And this matrix here, T, is the translation matrix. And there really isn't much more to say about it than, just to do a very quick calculation, just to assure yourself that that is indeed true. Because if you have a vector, x1, x2, x3, and a fourth homogeneous coordinate of 1, and if you multiply it by this translation vector, so 1, 0, 0 dx, 0, 1, 0 dy, 0, 0, 1 dz, 0, 0, 0, 1, when you carry out that matrix multiplication, what you get, well, look at what you get. You get x1 plus dx, x2 plus dy, x3 plus dz, and fourth row into the column, will give us a 1 there again. So that has moved the vector x, t times x. It's moved the vector x to something that we recognize as the vector x plus t. Okay, because this new vector has first component x1 plus dx, the second component is x2 plus dy, and x3 plus dz. So that is indeed the original vector x, which is being translated. Okay. So that's really all there is to know about translation vectors in three dimensions. Okay. There's not much to understand about it. Moving everything by some fixed displacement. Okay. Scalings are nearly as straightforward. If we want to scale everything about the origin, so rescale the length of all vectors, then if we want to do that by a scaling factor of r, then we simply multiply the four component homogeneous vector by this matrix X. Okay. So if you have a position in 3 dimensions and you multiply its 4-dimensional homogeneous coordinate vector by this matrix, it rescales it by the factor r. If r is bigger than 1, if r is positive and bigger than 1, your point is going to move further away from the origin by a factor of r. If r is less than 1 and positive, then it's going to move back towards the origin by that shrinking factor r. Less than 1. If the r is negative, it's going to do a similar thing if its absolute value is greater than or less than 1, but it's going to flip to the opposite side of the origin. Okay. So in particular, if the origin is here at my thumb, and I got a point here, if we're using the scaling factor r equals -1, well, that's just going to send the point to its exactly opposite point, opposite the origin. Okay? Because we're multiplying all the components of this by -1, so they all go out to the opposite side of the origin. Now, maybe you want to get a bit more sophisticated. Maybe you want to rescale by different factors in the x, y, and z directions. Well, that can easily be achieved just by varying the scaling factor r, the particular value in each of the columns. Okay. Okay, here's a good exercise. These are scalings about the origin. How would we handle, and this gives us a clue, this kind of leads us into the technique we're going to use for handling rotations. How would we handle rescaling about some other point C? What would that matrix look like? So I've got the origin over here somewhere, but there's some other point C, and what I want to do is rescale around C by a factor R. So let's say if I had R equals a half, I'd like to move this point X to this point here. It's a half closer to C. So let's say S is scaling by 1/2 about the center point C. So this point S moves to Sx here. S brackets X. And you know, this point Y out here, this should move to this point here, Sy. So things move twice as close to the point C. Well, the way we think about it is we don't try and tackle it directly by looking at the geometry around C and figuring out what to do to each of the components. We use a kind of cleverer way, which simplifies it and is much more suited to implementing these things on computer. Okay, so to get the matrix for X, for S, this scaling everything around the point C by 1/2. So I'm thinking of this being in 3 dimensions. I know it's only on the 2 dimensions in the page, but just a kind of descriptive picture. We think of S as a composition using the transformations we already have. What are the transformations we've already defined? Well, they're just the two that I've introduced to you just now, a few minutes, which are translations, so moving things around by fixed amounts, and scaling about the origin. Now, how does it help us, knowing about these transformations, to obtain the matrix for S? Well, we want to think of S as a composition, okay? Now, if all we can do is scale about the origin, and we want to scale about the point C, really, what we have to do is we have to move the point C to the origin. So how do you move the point C to the origin and do the same thing to every other point in the plane? Well, you want to do a certain translation. So you want to translate by minus C. You translate the plane by the vector minus C, then suddenly C has been moved to the origin. Then you can do your scaling by 1/2, scaling by 1/2 about the origin. I'm doing a composition of operations. Well, that will do the correct scaling. It'll move everything closer to the origin, which is now occupied by the point C, if you like. But then we want to move everything back to where it should be, okay? Because it shouldn't be centered around the origin. It should be back out at point C. So the point that's sitting at the origin is the point C, but that should be at its original location. And you get it out to its original location by translating by C. So we think of S as a composition of these 3 transformations. So first of all, we drag the scaling center point C, drag that to the origin, then scale about the origin, and then send everything back to where it, send it back to where it should be. So we send C back to its original location. So the matrix for S then is given by this matrix AS. And AS is just a product in the correct order. The order that we're using for the matrices, when we multiply them, must respect the order of the composition. So the last operation is to translate by C. So supposing C has coordinates C1 and C2 and C3, That's the translation matrix, but translated by C. We want to multiply that by scaling by a half, which is the diagonal matrix, a half, a half, a half, and 1. It's homogeneous coordinates. That's the matrix there for rescaling about the what is the zeros in there? 0, 0. For rescaling about the origin by a factor of half, and then the first operation was to translate by minus C. Well, that's going to be 1, 0, 0 minus C1, 0, 1, 0 minus C2, 0, 0, 1 minus C3, 0, 0, 0, 1. Okay. So that's what the matrix representing F is going to look like. Now, I'm not particularly minded to multiply them out, because it might just be the most boring time in your second year to watch me multiply those out. It'll take the rest of the period up to 5 o'clock probably. I'm not particularly interested in looking at it. I'm more interested in how we've constructed it methodically like that. If I ever need the actual matrix, I'll just get MATLAB to multiply it. I'm more interested in thinking about it as how I built up the general scaling transformation by using more basic ingredients. General translations and scalings about the origin. Okay. If needed, you can get AS using computer. Everybody get that idea of moving the thing so that the point of interest is at the origin, then doing the interesting thing about the origin, the scaling about the origin, and finally moving everything back. Okay. Means I only have to remember, I only have to deal with one basic kind of scaling matrix. And I'll build the other scaling matrices that I need by using the basic kind of scaling matrix and translations on either side. Okay. So good. Now this is going to motivate this kind of simpler example of scalings will motivate what we're about to talk about in terms of rotations. Okay. Any questions before we continue on? Good. Okay. So that was translations or scalings. Now we come on to rotations. Now, rotations in the plane, as hard as they were kind of pretty simple to think about. If the plane is the sheet of paper, to rotate the plane, what's involved in that is fixing the rotation center and rotating the whole plane about that rotation center. Okay? So you have a center of rotation, which is a point, and you have one angle. Just the angle describes the amount of rotation that you do. Okay? Conventionally, positive angles expressed in radians go anti-clockwise when you're looking down on the plane like that. Okay? Negative angles will go clockwise. Okay, but what's going on in 3 dimensions? Well, 3 dimensions is a jump up in dimension. So to describe a basic rotation of 3 dimensions, the center of rotation is now an axis, okay, which I'll represent by my pen. Okay, it's a line in 3 dimensions. Okay, so there's some axis of rotation. There's an infinitely extended line in 3 dimensions. And we're going to rotate space around that axis by a certain amount. Okay? So if I've got this axis represented by my red pen going across horizontally there, I can rotate the whole plane. I can rotate the whole of 3 dimensions by any angle around that axis. Okay? I can magically kind of lift you all up into the air and rotate the whole room around that. You'll go up there and I go down there and so. Okay? Or if I rotate it around this axis, around the center of the room, say, it's the central axis of the room, I could rotate you around, so you'd all suddenly spin over there, and I'd spin over there. Okay? If we specify the angle of rotation around that axis. So these basic three-dimensional rotations are specified by those two quantities, specifying the axis of rotation and specifying the angle. Okay. Now, there's a whole lot of different lines in 3 dimensions. Okay, there's infinitely many lines running through 3-dimensional space, and any one of them could be the axis of rotation for a rotation. So what are these rotation matrices going to look like? Well, I don't want to construct or think about a completely general rotation matrix that could have in it the specification of any axis of rotation at all in space and any angle. I'd rather try and identify a generating set of basic rotations, a basis of rotations, if you like, some small generating set of rotations out of which I could generate any general rotation. Okay. Now there's three obvious candidates around for special axes of rotation, and those are the coordinate axes, the x, y, and z coordinate axes that we already have to have. Okay? We already need the x, y, and z coordinate system to begin to talk about our 3-dimensional environment. So we may as well reuse those. So I'm going to introduce three special rotations, Rx, Ry, and Rz. And these are rotations, respectively, around the x-axis. Rx, Ry is rotation around the y-axis, and Rz is rotation around the z-axis. And this is what their matrices look like. Now remember how to think about this. Remember, in computer graphics, we have the left-handed convention. So your thumb is x, your first finger is y, the middle finger is z. And also the computer graphics convention is that y is the vertical axis. Okay? So y is pointing up in the sky. So the x and z are the axes that run parallel to the ground. In the normal, if we're thinking about a normal upright environment that we're standing in. Also, we need to, here. In general, rotations of a plane. So I'll just be general. I'll state AB. If I have some plane AB and I want to rotate to a certain angle theta. Now where's the third axis? Here there's only two axes. The third axis is coming off the page at me, represented by my pen there. Okay. So we're looking at these views typically, if we want to get precise and plot angles and vectors, we will often draw the paper will represent one of the planes in our environment. So to be able to see two of the axes, the third axis we'll normally imagine as the positive direction coming up off the page towards the eye of the viewer. Okay. Now this is represented. Actually, I want to use. Sorry, that has to be aerodynamics. This is represented by a 2x2 matrix. And you've got an A column, an A row, B column, B row. This is cosine theta, sine theta, minus sine theta, cosine theta. Okay, if I was just dealing with this 2-dimensional picture of an A axis and a B axis, so these are going to stand for X. The places of A and B will be taken by X, Y, or Z in the examples we're going to look at. 2x2 matrix that represents that as a linear transformation is this matrix: cosine theta, sine theta, minus sine theta, cosine theta. Theta is measured in radians, counterclockwise is the positive direction for theta. So when I'm looking at the first type of rotation, so when I'm looking at Rx, what's the picture going to look like for Rx? Now, this is where you need to get your left hand out. Do the axes with your fingers. So when we're rotating around the x-axis, we're going to imagine the x-axis coming up off the page towards us. And what we see then is the y and z-axis. So the z-axis is running here, the y-axis is running here, and the x-axis, the positive x-axis, is towards the viewer. Okay, the positive x-axis is my pen. Okay. The positive x-axis, so what we see then is remember it's x, y, z, the thumb, index, and middle fingers. So when x is coming towards you, you can see y and z lines. So that means the matrix for rotation around the x-axis by an angle theta, that's 4 by 4, so make it kind of big. You've got x, y, z, and the homogeneous coordinate. And the columns are labeled x, y, z, and the homogeneous coordinate. So we got to repeat this pattern here of the cosine theta, sine theta, as regards to AB here, but this time as regards to Z and Y. Okay. So what we end up with is, here you can see we're going to have a 1, 0, 0. Yeah, and the reason we have a 1 there is, see, what happens to the points along the x-axis? When you rotate around the x-axis, what happens to the points on the x-axis? Well, they stay exactly where they are. So if you've got a point on the x-axis, but you're rotating 3 dimensions around the x-axis, each of those points on the x-axis just remains exactly where it is. Okay? So that's why we have this 1 in the x-axis entry. And then we're going to have 0 cosine theta, I mean, just as it is in the notes, sine theta 0, minus sine theta, cosine theta 0, and 0 there, and then the fourth row is this usual homogeneous row to repeat the homogeneous coordinate. So this is just applying this 2 by 2 pattern here for general A and B axes to this picture that we can see here, where we're rotating around the x-axis by some angle theta. And we get very similar pictures for the y, ry, and rz. Okay? So they're given there in the notes. So those specific matrices in the notes are generated using this generic picture for a pair of axes A and B, and just by looking at the picture you get for ry and rz. So when you want to rotate around the y-axis, what do you see? So your y is your index finger, so when you point your index finger towards you, kind of looking like that, it's got x coming off to the right and z going up the page. So the picture you see when the positive direction of y is coming towards the viewer, these are how the axes look. Okay? This is using the left-hand system. If you use the right-handed coordinate system, it'll look wrong. So use your left hand. If you use the right-hand coordinate system and point y towards you, you will see z will be down here, and x will be up there. It's difficult to point it towards you. So point it towards your neighbor and ask them what they see. Okay. And then similarly for rz, so if you point z towards you, positive direction of z towards you, just like that, then x is going up the page and y is going to the right. Okay. Does that make sense? So these are 3 special kinds of rotations. Rotations that go around these special rotation axes, which are the coordinate axes, the x, y, and z axes. But they're special rotations. In general, you could have any axis whatsoever in 3 dimensions, say my pen, just going along one of the coordinate axes. if you think of the coordinate axes in standard, well, it's not a rectangular room, but being in the corner of the room, so the two directions of the floor and the vertical direction up, this axis is not in any one of those, only it's a linear combination of all three. So what we'd like to get to is some standard way of describing any rotation using these standard ones. Okay. Now, a bit of terminology, or any questions? Now, it can be a bit difficult to, there's left-handed thing to know, there's the various conventions to think about. So, there's a lot to think about, and you need to tread quite carefully when you're constructing programs using these or performing calculations using this. You got to check and recheck again. Okay. Now, there's some standard terminology here. It isn't used so much in computer graphics, really, but you'll may be familiar with it about if you've ever, anybody ever flown, right? Cool. Roll, pitch, and yaw, do they talk about that all the time? So these are important. So obviously, well, I should hand it over to you. When did you fly a plane? Oh, cool. Excellent. And you took the controls yourself? Yeah. Well, okay, I hesitate to talk on about it since there's obviously someone who's more direct experience in the class, but you're flying a plane, you need to be able to control the rotation of the plane and also be able to specify what the rotation is or report what your rotation is. And you need to have a very clear understanding about three-dimensional rotations if you're designing, flying, or doing anything with planes. So there are these traditional terms, roll, pitch, and yaw. You might also be familiar with them from sailing as well. I'll talk about the roll, pitch, and yaw on a boat as well on the ocean as it gets rotated. So the roll is, well, when you're flying along like this, roll is doing that, isn't it? Feel correctly. Pitch is when you go up, fly up or down. This is hilarious, isn't it? And yaw is when you say, well, I won't fly to Manchester, I'll fly to London instead. So that's a yaw rotation. Yeah. Okay. The roll is when the plane rolls from side to side. Pitch is when it goes up or down, and yaw is when it changes direction to fly to a different location on the ground. So to speak. Okay. So there's a vertical axis coming down from the plane. So rotating around that is a yaw. The axis through the plane from head to tail. Rotating around that is a roll axis. And then the pitch axis coming out perpendicular to the roll axis, rotating around that is a pitch rotation. So that's how the terms roll, pitch, and yaw relate to a plane, an airplane. Similar definitions as they pertain to a boat, ship. They're sometimes used in computer graphics as well. And the convention there is, I have to remind myself, so roll is around the z-axis. Yeah, so we normally think of, if you think about the conventions about the screen, the computer screen, remember x is the horizontal coordinate, y is the vertical coordinate of the screen, and z is the coordinate that disappears into the screen. I think if you're flying a flying simulator, the z-axis, so you're looking at the front of the plane, the z-axis is pointing in the direction that the plane is going. Okay? So rotations around the z-axis will be roll rotations. Flying the flight simulator and you rotate around the z-axis, which is disappearing into the screen, that's doing a roll rotation. If you rotate around the y-axis, around the vertical axis, you're changing the direction the plane is flying in relative to the ground. So that's a yaw. And the pitch axis, which is coming out to your left and right as you look out the cockpit of the plane, well, if you rotate around the x-axis, so the x-axis stays where it is, everything rotates around it, you're either going to fly down towards the ground or up in the air. Okay? So that's the terminology of roll, pitch, and yaw. Did I say anything vastly incorrect there? No? Good. Got the seal of approval. So you still fly? But no? Okay. Do you miss it? Yeah. Anyway. Okay, how are we doing? So we got these special rotations, rotating around X, Y, or Z axis. How do we describe a general rotation? Well, just as we did for describing a general scaling, we first described a special scaling about the origin. And then we were able to describe a general scaling by dragging everything to the origin using an appropriate translation, doing the scaling about the origin, and then sending everything back to where it should be using the inverse translation. We do a similar kind of thing with rotations. So here's a general problem. I want to rotate around that line. So there's a vector D, which is going from a reference point P in some direction. So this could just be any arbitrary line in the three-dimensional environment. You specify some reference point on the line, say the tip of the pen here, and you specify a three-dimensional direction vector D, which indicates the direction of the line. Okay? So reference point and a direction vector specifies a line in 3 dimensions. And let's say I want to rotate around that line by some angle. We want to rotate by an angle theta around that line now. Okay, again, what I'm not interested in is figuring out exactly what the matrix looks like. Instead, I think of it as a sequence of standard transformations which we've already gone to the trouble of defining. Okay? So these are the steps. First of all, the line, the rotation axis, typically it's far away from the X, Y, and Z coordinate axis, right? So what we want to do is we want to get it to the origin. So when I take your line and somehow drag it back to the origin, because things are easier near the origin, you're closer to your standard rotations. So the first operation is to perform a translation, to drag the line L so that it does go through the origin. Now, is there anything in what I've said that tells you what translation to use? Well, yeah. If the line has been specified, you will know a reference point on the line. So if we translate by minus P, P is the position vector of that reference point, we translate by minus P, that drags the line so that it does go through the origin. And we know about translation matrices. We then go through what's known as a rotation sequence. Now, the order specified here is not unique. You can do it in a number of ways, but this is a usual or traditional sequence to use. So it's a yaw roll rotation sequence. So let's think of the origin as being at this corner point of the table here. Okay. So that's the y-axis. So if I'm using the left-handed rule, this edge of the table is x-axis, this edge of the table is the z-axis. And then the y-axis is coming up vertically like this. Okay. Now here's my general rotation axis out here in space somewhere, with a reference point P at the back of the pen. So I first perform the translation by, let's say it's pointing like that. I first perform the translation by minus P. So that brings the vector back so that it is now, or it drags the line back so that the line is now going through the origin. And here's the rotation sequence there. I then perform a yaw rotation. So the y-axis is coming up from the corner. I rotate around the y-axis, and I rotate it in such a way so that the vector is then, that the line is lying in the y-z plane. So I rotate it so that it's lying above the z-axis. That the line is lying in the y-z plane. So that's a yaw rotation, rotating around the y-axis. Then I rotate it down so that the line lies exactly on the z-axis. I do that by rotating around the x-axis, doing a pitch rotation. Your pitch, performing a pitch rotation. Now, the line L, which I'm supposed to be rotating around, is now going along the z-axis. So now I rotate space around the z-axis by this angle of theta. So this is step 3. Perform the actual rotation by the angle theta that I'm interested in. And that's going to be a roll rotation, rotating around the z-axis. So space will get rotated. But now everything has been moved around and it's in the wrong position. Remember, I originally wanted to rotate around that line by the angle theta. But I've dragged it here, I've rotated it here, I've rotated it there, and then I've rotated it here. So now I want to undo those first few steps I did. I have to undo them in the reverse order. So I rotate everything around the z-axis, then I undo the pitch rotation, I undo the yaw rotation, and then undo the translation rotation, sending the line back to its original position. But because of the z rotation by angle theta, everything else will now be rotated by an angle theta around the original rotation axis that I wanted to rotate. Okay. So that's the rotation sequence. Okay. Here we specify, so those 5 steps, 1, 2, 3, 4, 5. The next position, the notes, we grab and construct the transformation matrix for each of those steps. So the first step I want to translate by minus p, there's the translation. Then I want to do the yaw rotation, rotating around the y-axis. There's a diagram on the other page which shows the direction vector d of the line, and it'll have components dx, dz, dy. V is the length of the projection of d down onto the xz plane. And just by looking at the triangles and looking at the angles and looking at the ratios of sides, we can see that for this one anyway, so this one is pointing in the positive quadrant. It's pointing up in the, octant of 3 dimensions. It's in the positive octant, so the positive x, positive z, and positive y coordinates. At least for this one, the sines and cosines we can just form out of ratios of dx, dy, dz, and v. Where v is the length of the projection of d to the xz plane, and the scalar quantity d here is just the magnitude of the vector. So we can form ry and rx carefully. Then we form rz. So rz, we're using the angle theta, which was specified as part of the original problem. Because the original problem said rotate space around the axis L by an angle theta. So there's the rz axis. So these rx, ry, and rz matrices are following the pattern specified out here. There they are. And then we just need the inverse steps. We want to undo, and we translate the line so that it goes to the origin. You do your rotations here over the z-axis, so the pitch rotations here on the z-axis. You rotate by theta. Then you want to undo those all. So you want to do the inverse pitch rotation, the inverse yaw rotation, and the inverse translation. And if you've already constructed the matrices for translation, the yaw and the pitch rotations, then you just simply use their inverses. And so this general rotation matrix R is now given as this very long product. So this is like the full translation and rotation sequence that can represent a general rotation. Okay. Remember, you read this as a composition of transformation. Well, it's written as a product of matrices, but you can also use it, interpret it as a composition of transformations. Yeah, I should have said that. By now, I'm being a bit sloppy with the notation in that I'm not carefully distinguishing between the transformation and the matrix that represents it. I'm beginning to confuse those two terms because really they're very synonymous. Okay, so a transformation, or the matrix that represents it with respect to the x, y, z axes, I'm kind of confusing the two because they're, to all intents and purposes, kind of the same thing. So reading this composition of transformations, translate to the origin, yaw rotation, pitch rotation, the actual z rotation by theta that we're interested in, and then we undo each of those operations. So inverse pitch, inverse yaw, inverse translation moves everything back to where it was at the beginning, except it will have all been rotated around L by an angle phi. So there's a few minutes now remaining in this first session. What I'd like to do is demonstrate this. Oh my God, how are we going to demonstrate it? Well, I'm going to use our old friend MATLAB to demonstrate it. And this introduces elements of the way you're going to want to handle these things when it comes to the village assignments. Okay? I've got a pre-prepared program here, 3D here, which I'll just show to you. Before we look to this, any questions or queries about what we just looked at? Just increase the size here. Bear with me for 1 minute. A bit harder than it should be to increase the font size. Should be, probably is an easier way, just another way. Is that big enough? Yeah. Okay. In order for us to understand what I'm talking about here, I just need to tell you a few things. So this is what we're going to do. We'd like to imagine a cube. Okay, very rough picture of a cube here. And what I'd like to do is, I'd like to imagine the rotation axis as being the one that joins a pair of opposite corners of the cube. Opposite corners of the cube. And what I'd like to do is rotate by an angle theta, rotate the cube by an angle theta. Right, so here's the cube. Pairs of opposite corners there, my thumb and finger. So what I'd just like to model, or what I'd like to get MATLAB to do, is just to rotate the cube. So I keep those opposite corners fixed because they're at my fingers. I'm just going to rotate the cube like that around that axis. Okay? So that line, the line that joins those opposite corners of my thumb and finger, that whole line is remaining fixed in this rotation. Okay? So the 2 points aren't moving. Everybody see that? Okay. Now we need to make things exact for MATLAB. So there's the X and Z axis. I'm going to talk about this cube here, which is at position, so its vertices are there at positions 2 and 3. So that's going to be the bottom of it, if you like, the bottom face. Now I'm going to imagine that being held at y equals 1, I believe. And then the top face, it's the bottom face, at height 1. The bottom face will be at y equals 2. So, yeah. And I'm going to label my vertices as vertex 1, 2, 3, and 4. So those are the 4 vertices around the bottom face. And then so this whole picture here is at y equals 1. So this is all remember the y-axis is coming off towards the viewer. I'm specifying that this is the plane at height y equals 1. And I'll add a separate plane at y equals height 2, which is the top face. Again, those vertices at the same positions on x and z. This is y equals 2, and I'll number these. So these numbers in the circles are just labels. Labels for the vertices. Okay, so e.g., the homogeneous coordinates of vertex 1 are Remember, it has to have x, y, z, and a last homogeneous coordinate of 1. Well, you see, its x coordinate is 2, its z coordinate is 2, and it's at height y equals 1. So 2, 1, 2, 1 are the homogeneous coordinates of vertex 1. And the other 7 vertices, you can similarly read off their coordinates. Okay? So that fully specifies the cube. And this axis is going to go from 1 to 7. Isn't it? Those are going to be the. So I'm telling you that I want to rotate this cube around the axis that goes from vertex 1 through vertex 7. So those are opposite vertices. This 1 is at the bottom left corner, like here, and 7 is at the top right corner, in the top face. I want to rotate around that by an angle theta. Okay. And I've got a prepared MATLAB program that will do it, and we'll be able to view the results by doing some three-dimensional plots. Okay. Any questions about the setup, please? Okay, about the setup of that. Okay, everybody got that? Go back to the MATLAB. So there you see cube verts. Cube verts is the array of vertex coordinates. You see the first column there, 2, 1, 2, 1? That's the first column of homogeneous coordinates I wrote down. You just have that on your page for vertex 1. So it's vertex 1, vertex 2, across to vertex 8. So those are the homogeneous coordinates. Remember, y is the second coordinate. So the first 4 vertices are at height y equals 1. They're the bottom face of the cube. The second 4 vertices are at height 2. They're the ones, the top face of the cube. So that's my cube. What is cube polys? You see, cube verts just specifies those 8 vertices of the cube. Cube polys specifies each of the faces of the cube. How many faces does a cube have? 6. 6 faces to the cube, top, bottom, and the 4 sides. These rows here are sequences of vertex labels. I'll make this file available afterwards as well. So what we're seeing here in the rows are sequences of vertex labels. So 1, 2, 3, 4 is the bottom face. 5, 6, 7, 8 is the top face. And then 1, 2, 6, 5, that's one of the 4 side walls. And the other four middle rows are each of the other 4 in total, 4 side walls. So that data fully specifies the cube. So it's sitting up away from the origin. If we can imagine the origin here, again, this is sitting up here. It goes from height y equals 1 to height y equals 2. And its coordinates are at, the vertices are at positions 2 and 3 on the x and z axis. So the cube is approximately there in space, with the origin at this back corner of the table. Okay? So that's where the cube is. So imagine it levitating there. What I want to do is I want to do a rotation. For you guys over there, I want to do a rotation like that. You guys over here to see, so I'm fixing that axis. I want to do that kind of rotation. I want MATLAB to do that for me, using what we set up here. Okay, yeah, at the moment it just, we won't look at this in detail, but basically I have a loop here from I equals 1 to the number of polygons. So this goes through the 6 faces of the cube. It sucks out the coordinates of the vertices, and this fill3 command, x, y, z, this plots a polygon. So this fill3 command gets executed 6 times, and this is the one that plots the 6 faces of the cube. So when I ran that there, when I ran that there, I got this 3-dimensional thing. And so that's a proper 3-dimensional plot. So let's go back to this kind of square. We can rotate that in 3 dimensions. So there's my actual cube in space. Okay? So that's the original cube, the one I was holding up above the table there a moment ago. So let's go about trying to rotate that. Now, just as before, I've written helper functions. So I've written a rot matrix X function. a Rot matrix Y, and a Rot matrix Z. They take one argument theta, which is the angle, and they just return the appropriate rotation matrices. So those are functions that implement the rotation matrices on page 33. So page 33, I've just got one little function for each of those, which I'm going to use. And then I have this trans matrix, dx, dy, dz. That just gives me the 4x4 homogeneous translation matrix by the amounts dx, dy, dz in the x, y, and z directions, respectively. Okay. So at the moment, that's all the program does. There's this numpolys loop, which executes the fill command 6 times, once for each face. So now we want to get rotating. So I've hidden it down here in storage. So I'm going to take all this. Now, okay, it can be hard sometimes to just stare at MATLAB code in a class, but I'll just highlight the important aspects of it and persuade you that it is implementing what we just described with our translation rotation sequence there. So the first transformation I grab is transmatrix -2, 1, -2. Because the coordinates of this back vertex of the cube, the one closest to the origin, is 2, 1, 2. So I'm going to translate by -1. So that's going to take the original cube and bring it back to there, to place it at the origin. Yeah, so that the vertex 1 of the cube is now exactly on the origin. That's what that is. Then I have this D vector, 1, 1, 1. That is the vector which points along the axis. It's this vector going out here. The vector somewhere along it here. The appropriate length is 1, 1, 1 on the x, y, and z axis. So this is the vector. The vector 1, 1, 1 is the one that points from the origin out through that opposite vertex of the cube. Okay. These lines, here I get the angle theta from D1, D3, and V. So those are the parts of D1 and D3 are the dx and dz. So they're both 1 in this example. V is the square root of the sum of the squares. So V is, as in the notes, the length of the projection of that vector down onto the xz plane. So this command here grabs the angle, the required angle for the pitch rotation, no, for the yaw rotation. The rotation that moves the rotation axis so that it lies above the z plane. Remember, the cube is like this now after translation. The yaw rotation rotates it around so that it's exactly like that. The rotation axis that I want to rotate around is now pointing up this way. So it's lying directly above the z-axis. I then, using this command phi here, phi grabs the angle that I need to rotate down by, which is a pitch rotation. And you see there, I rot matrix x by -phi, because this is going in the clockwise direction when you look at the z-y plane. From the positive x direction, you see you have to go clockwise. So that rotation, Rx there, rotates it. Well, I can't force the thing through the table, but if I translate it out to the side, well, it started like this, it rotates it around like this, and then it rotates it like this. So the axis that I wanted to rotate around, this one, is now lying exactly along the z-axis. Then RZ is the actual rotation I want to achieve. I've just stuck in an angle here, 2 pi over 6. I'm just choosing that arbitrarily as the rotation, 2 pi over 6 that I want to rotate the original cube around its axis. So then you see this matrix A here. So this is following the matrix product at the bottom of page 35. Translation, yaw, pitch, roll rotation, the actual by 2 pi over 6. And then in putting them back, okay? Inverse inverse pitch, inverse yaw, and inverse translation. So A is the overall, A is the rotation matrix. So I take my original cube vertices and I rotate them by multiplying. I rotate them by multiplying by the matrix A. Okay, sorry guys, just stop. Thank you. So this gives me a new set of vertices, rot cube verts. So by multiplying by that matrix A, I'm changing these nice vertex coordinates at the very top of the screen. They'll change to some new values. Should probably take a look. Which is where they go to when you rotate the cube around that axis from its bottom corner to the opposite corner by 2 pi over 6. And then I get the program to just go through exactly the same plotting routine. This another numpolys loop, which plots the 6 faces. And this time I'm going to plot them with edge color R. So that will plot it in the red edges as opposed to the black edges of the original one. And it will superimpose the 2 cubes. So when I run this now, I press it. So that looks correct. Yeah. You can see the original cube in black. And there's the rotated cube red. Now, if you look at it, this bottom vertex is the same for the red and the black cube. And its opposite vertex, opposite it, is also the same. If I rotate it around here, you'll see that opposite vertex, which is lying at the top of the screen now. You see that coincides exactly with the black and red cube. And the bottom vertex, excuse me, at the bottom of the screen, that's exactly the same for the red cube and the black cube. Okay, so that's a kind of typical view of the XYZ axis. You can see the original cube and the rotated red cube. But what MATLAB actually did was well, you can think of it, what was going on with the matrix products there. It dragged it to the origin, spun it around the y-axis, spun it around the z-axis, then it did the 2 pi over 6 rotation. And then undid the rotations and the translation to send it back to its original position. But it didn't actually do that. It actually did it all in one step by multiplying by the matrix A. But the matrix A was assembled out of those steps. So if I take that angle 2 pi over 6, take it back to something smaller, 2 pi over 12, rerun it, you should just see the 2 cubes with the red one only just barely rotated. Rotated, and so I'll shrink it, make it even less, 2 pi over 6. You may not even be able to notice that. That's 1/36th of a full turn. Okay, so there's the black cube, and the red cube has just been ever so slightly rotated. Okay. Okay, so that's our first look at 3-dimensional rotations.